Hello, welcome everyone. I'm Avidanjang Thapa, Staff FPGA Design Engineer at LogicTronix. This is the webinar on Introduction to Versal, where we're going to specifically focus on Versal AI Edge series for its application in ADAS. This is the general outline of this session. We're going to first start with Introduction to Versal, then move on to the Versal portfolio, Versal architecture, ADAS system case study, and then finally mostly asked questions. So the Versal portfolio, there are 5 devices in the Versal portfolio: Prime series, AI Core series, HBM series, AI Edge series, and Premium series. Prime series, AI Edge series, and Premium series have generation 1 and generation 2 of these devices. Gen 2 is the newer of these devices. The advantages of Versal AI Edge architecture are shown here, specifically 6 of the highlight advantages. Versal AI series architecture contains 3 compute domains on a single die. It contains PS, PL, and AI engine, which work together in tandem. Programmable network on chip with integrated DDR memory controller. It also has built-in functional safety and security with some of the components rated for ASIL-B. It has purpose-built AI ML tile array with native ML data types targeted specifically for machine learning workloads, flexible sensor integration via programmable logic, and complete edge application acceleration on a single chip. You can design a whole application using this single chip for different compute workloads. So this is the Versal architecture. On the right side, we can see the high-level block diagram. Versal contains 3 different compute domains: scalar engines, adaptable engines, intelligent engines. Scalar engines are the ARM Cortex general processor and ARM Cortex real-time processor. Adaptable engines are the programmable logic or FPGA. Intelligent engines contains AI engines for vector workloads, and DSP engines specifically targeted for signal processing. The real architectural benefit of Versal devices is the network on chip. This replaces the AXI crossbar with a programmable quality of service aware interconnect. NOC connects the AI engines PL, PS, DDR, PCI without routing through APU memory system. In the previous Zinc MPSoC architectures, memory access were done through the AXI HP ports, due to which sometimes there will be contention for the bandwidth in different computing workloads. The bandwidth isolation between different for example, say sensor DMA and inference data paths is architecturally guaranteed in the NOC, and it is not software managed. Everything is fully implemented on the silicon, and the aggregated peak bandwidth can reach up to 100 gigabyte per second across the whole NOC fabric. The processing system contains APU. This is the general processor which can host the Linux operating system and general host applications. It contains dual core ARM Cortex A72 processor which has access to up to 48 KB instruction cache and up to 32 KB data cache. So instruction cache has parity, while data cache comes with ECC feature. It also has a Neon SIMD engine and single and double precision floating point units. For the management and control, it has 2-stage memory management unit, and it supports multi-threading, multi-OS applications along with Versal memory mapping. The interrupt handling in APU is ARM GIC 500. Next is the real-time processing unit in the processing subsystem. It is a dual-core ARM Cortex R5 F processor which has access up to 32 KB instruction cache and up to 32 KB data cache. In this, both instruction cache and data cache are ECC capable. It also has access to up to 128 KB TCM for each core. So total is 256 KB of tightly coupled memory, also 256 KB of on-chip memory. along with access to DDR memories as well. RPU is located in the low power domain, and it can interact with the APU's L2 cache via either OCM or DDR memory. RPU has two modes, split mode and lockstep mode. Split mode can be used for the high performance, in which each core acts independently, and in the lockstep mode both processors checks each other's outputs, and this is utilized for functional safety and reliability. The PMC is the platform management and controller that controls and monitors the Versal devices and its different configurations. PMC is responsible for device configuration, security and device integrity, testing and debugging, and system monitor. On the right side, we can see the high-level block diagram of the platform management controller, and it has various components like ROM code unit, platform processing unit, its own RAM, and a system monitor with its own real-time clock. For more in-depth detail, we can check the technical reference manual of Versal, which is AM11. Then we also have processing system manager in the Versal. It is a different component which is 32-bit TMR microblaze processor. It is also located in the low power domain, and its specific function is to control the different power islands. So there is low power domain, battery domain, full power domain, PMC power domain. So each of these power islands are controlled through the processing system manager. The general boot order in the Versal is the PMC first initializes the Versal device via the boot pins and PLM. PLM is the platform loader manager execution program. The PMC initializes the specified Versal blocks like AI engines, PL or PS, after which if the PS initialization is requested, the PMC starts processing system manager to up that full power domain. The PLM downloads the firmware into the PSM RAM for the processor to execute. Knowing the boot order of the device helps us during the debugging. In case when you bring up the device, there is a hang up in any specific section. Coming to the adaptable engine or programmable logic. So this is the FPGA portion in the Versal. It provides flexible programmable hardware logic for parallel and deterministic processing. On the right side, we can see the columnar architecture of the configurable logic blocks in the Versal. So each CLB contains 32 lookup tables and 64 flip-flops organized into 4 slices. There are two types of slices, L slice and M slices. L slices can only be used for logic implementation or lookup table, while M slices can be used as shift register or distributed RAM or lot RAM. Each slice contains 8 loss positions from A through H, with a flip-flop for each of the lookup tables. It also contains IMUX register to improve the timing closure. Compared to the previous UltraScale architectures, the Versal CLB tile is completely redesigned with, like I previously said, 32 lookup tables and 64 flip-flops, while in the UltraScale, the CLB contained 8 lots and 16 flip-flops only. Each lookup table and flip-flop now has 3 outputs instead of 4, which increases the routability of the logic implemented. It also has dual lot mode, which can implement 2 separate logic functions and up to 6 independent inputs. In the routing side, the lot-to-lot cascade paths inside the configuration logic block cuts the multiple levels logic delays and reduces the routing pressure. The SSL connections are now built inside the CLB, and signals inside the tile are registered rather than in a specific columns. Also, the IMUX registers are embedded in the CLB, which improves the critical paths, and we can get a higher Fmax or maximum frequency, and reduce or fix hold violations in many cases. Coming to the logic functions, the wide function multiplexers like MUX F7, F8 and F9 in previous architecture has been removed. This wide multiplexing is now done using the standard lots combination instead. New cascade multiplexers allow carry chains to start from bit positions 0 and 4, and we have clock enable level of granularity, which remains same as in the previous architectures. On the memory side, half of the lookup tables can be used as lot RAM or shift registers, and these lot RAMs have a dedicated support for 32-bit and 64-bit depths. Then we have another computing domain called intelligent engine, which contains AI engines and DSP engines. AI engines are tailored for high throughput, low latency, and power efficient vector workloads. AI engine is an array of a vector processor with SIMD vector units, and it has instruction and data level parallelism. AI engines are specifically targeted for the machine learning workloads. DSP engine is a newer architecture called DSP 58 and has a lot more functionalities. Both AI engine and DSP engines are complementary to each other. Coming to the AI engine is a 2D array of AI engine tiles, each operating in an independent systolic manner. On the right side, we can see the layout of the array and its interfaces and connections. This block diagram is specific to the Versal AI Edge series Gen 1 devices. For more in-depth, we can check the architecture manual 20. So each of these tile communicates to each other through 3 dedicated memory interfaces. Memory interface, which are direct tile to tile between adjacent AI engine tiles, through XI4 interconnect, which connects to AI engine array to the PL, PS, and DDR using the NOC routings, and cascade interface, where data passes horizontally between the tiles for different sequential or chained operations. So the number of tiles is dependent on the device variant, and it can range from 8 to 304 AI ML tiles in the Gen 1 Versal AI series devices. So these AI engine tiles are programmed using C, C++ language. Coming to the array architectures, the array layout is as shown in the right. Each array contains a local data memory so that data stays very close to the computation unit. Local distributed memory eliminates the cache misses, and each of the compute implemented for in a specific AI engine tile can access faster the local memory. The data movement paths is solved through 3 different ways, like I previously mentioned, cascading through local memory access and XI4 interconnect. Then coming to the specific AI engine architecture, the AI engine tile contains a scalar unit and vector unit. Scalar unit is a 32-bit scalar RISC processor, and the ALU of this scalar unit contains 32 by 32 scalar multiplier, and it has 3 address generator units. 2 are used for load units and 1 for storing. The vector unit is good for concurrent operations on multiple vector lengths, and it has a full permute unit with 32-bit granularity. It contains 1024 bits of X operand and 256 bits wide G operand. For more details, we can go to the architecture manual 20. DSP engine is the newer architecture, DSP 58, which is shown at a high level block diagram here. So this is the 6th version from the AMD, and it is also backwards compatible with the DSP 48E2. So any of the applications implemented in the DSP 48E2 can be migrated easily to the DSP 58 architecture. So it can be considered as a superset. So it has 4 modes of operation: scalar fixed unit, vector fixed unit, complex 18 by 18 MAC mode, and a floating point arithmetic mode. So native floating point operations are also supported. Network on chip, or NOC, is the main highlight of this chip. It is a XI interconnecting network for sharing data among different compute units like PL, PS, and other integrated blocks like DDR, PCIe. It is very high speed and has horizontal and vertical pathways for fast communication. The network on chip is directly implemented on silicon, which ensures timing reliability and also reduces the power consumption compared to routing through the programmable logic. We should also know some of the terminologies that are required to understand the network on chip in the Versal. NOC means the network on chip, the whole fabric. NMU is the NOC master unit. Through the NMU, the data enters into the NOC pathway. Then we have NSU, which is the NOC slave unit. It is the egress port. Through NSU, the data exits from the NOC pathway to the programmable logic or other compute domains. NPS is the NOC packet switch, which routes different packets to the different NOC destinations and connects the source to the destination in the different compute domains. It is like network routing we have in the internet. And NIDB is the NOC inter-die bridge. This is in the different some of the Versal chips. DDR-MC is the dedicated DDR memory controller, which are directly hard IP on the Versal devices. So integrated DDR-MC or DDR memory controllers are the hard IPs which are connected to the NOC. So if we need to access the external DDR memory, we have to connect it through the NOC. This is a mandatory process in the Versal. In the devices which has hard or which has integrated DDR-MC. In the previous architectures, the DDR access was routed through APU memory subsystem or some soft XC interconnect, which consumed the PL resources and added the latency. This has been improved, and now PL resources can be saved in the Versal devices. So the key benefits in the of having integrated DDR-MC is removes the soft interconnect logic previously needed to reach the DDR, freeing the PL resources. It supports up to 4-way interleaving across different memory controllers. In some of the devices like VCK 190, we have up to 3 memory controllers. NOC quality of service controls and prevents bulk transforms from starving during time sensitive applications or workloads. It also supports ECC for reliability in safety critical applications. In this diagram, we can see two of the designs device view. On the left, there is design without NOC, and on the right, there is design with NOC. We can see that there is up to 50% PL resource saving when NOC has been used. So in the one of the design, the total resource utilization was 70,000 lots and 70,000 flip-flops, out of which 37,000 lots and 42,000 flip-flops were used for the interconnect, which is shown through the pink color coding. And by moving this interconnection and routing the data through the NOC, we are able to conserve 50% of the PL resources, which is a huge boost in our in the ADAS application. So that was the general overview of the Versal AI Edge series architecture. Like I previously mentioned, Versal AI Edge series architecture has two generations, Gen 1 and Gen 2, and in this table we can see the improvement in Gen 2 from the Gen 1. The application processor APU has been replaced with ARM Cortex A78 automotive grade ARM cores, and depending on the devices or Versal variant, we can get up to 8 cores. RPU has also been upgraded to 10 core up to 10 core ARM Cortex R52. The platform management controller previously had triple redundant PMC, but now a separate application security unit has also been added. Coming to the AI engines, the AI engine architecture has also been improved to the V2 architecture, and one improvement is the added support of the data types. In version 1, there was only Int8, Int4 and BF16 data types supported, and this has been extended in Gen 2 with FP8, FP16, MX6 and MX9 data types. All these data types are natively supported. On the DSP engine side, the DSP58 architecture remains same, but the number of slices has been increased up to the 2064. The external memory support was previously, it was only up to DDR4, while in the Gen 2 it is up to DDR5. Now specifically regarding the hardware integrated IPs available in Gen 2 were limited. So the advantage that Gen 2 brings are specifically beneficial for the ADAS application. Like image signal processor, there was no hard ISP in the Gen 1, so we had to instantiate PL ISP. But in Gen 2 there is hard ISP present, which supports up to 4K 60 FPS input, and the video codec unit in the Gen 2 could only do the decoding. There was no encoding support. Now Gen 2 has full VCU version 2 which supports both encoding and decoding. Gen 2 also adds a graphics processor ARM Mali G78, and a hard display port 1.4 controller IP has also been added. The PCI support has been up to Gen 5, and the NOC architecture is also version 2 with newer supported features. On the functional safety side, previously only ASIL B rating was for few of the components in Gen 1. In Gen 2, this has been upgraded to support ASIL D, SIL 3, ASIL B, SIL 2 for different components. Some of the components support up to ASIL D, while some of the components are rated till ASIL B. On the security side, also previously mentioned, application security unit has been added. So now coming on to the ADAS system case study. So this is the ADAS system that we are currently working on. As you can see, the high level architecture is shown on the right side. So it has up to 4 drive assist camera, 4 park assist camera. All of these are connected through GMSL to link to the device. We have a LiDAR for Ethernet based point cloud support, GPS plus IMU, and ultrasonic array. And CAN bus is used for vehicle ECU interface. We also have an MIPI output for an FPD display, and a 10G Ethernet link for data logging. All of this system is being designed on the single Versal Edge AI series chip. Firstly, currently we have developed in the Gen 1 series of devices, and next we are going to migrate it into the Gen 2 devices soon. So next is the ADAS system architecture high level block diagram. So let's take a moment and go through the different color coding before we get started on this. So blue components or blue blocks are implemented in the PL, yellow blocks are implemented in the AI engine, green blocks are implemented in the processing system, and light blue blocks are the sensor interfaces. So if we start from the left, we can see that GMSL2 cameras feed an external deserializer which sends MIPI data into a MIPI IP and data splitter in the PL. The streams split into 2 paths: the main drive assist pipeline and the park assist 360 view, both running through PL pre-processing before they can reach the AI engine. The central region within the dashed line is the AI engine section. All these components are within the AI engine. On the upper path, we have ML runners which execute the detection models, object detection, light detections. These are done using the Vitis AI library. On the lower path, we have LiDAR pipeline which runs range image to point cloud conversion, connected components labeling, ground labeling, and segmentation. As you notice that everything that goes to the AI engine is routed through the PL first. The PL handles the protocol and timing, and then the AI engine receives structured data, not the raw sensor streams. Now moving along to the right, the results from the AI engine go through the post-processing and visualization, then a video mixer and HDMI transmitter to the display at the end. The sensor fusion core in the PS aggregates everything and produces the final output. The LiDAR enters through a UDP socket and PL captures it, and the GPS and IMU enter to the PS. So all of this data routing is done through the network on chip. So the workload distribution of the ADAS system architecture that we just saw, we have here arrange the data in the table which segmentation of the each different domain. For adaptable engine, the components that are implemented in PL are GMSL2 deserializer, MIPI, data splitter, ISP pipelines, pre-processing, ultrasonic processing, ADAS 360 park assist, LiDAR raw capture, and the CAN-FD interface. All of the sensor entry points are in the programmable logic. In the AI engine column, we have implemented custom kernels for the LiDAR change, range to PCL, connected components labeling, vector angle and distance calculations, ground labeling and segmentations are custom kernel implemented in the AI engines. Then we have also used Vitis AI NPU, which is implemented in the AI ML array for the CNN inferences. The CNN and inferences that are done are object detection, traffic light detection, LiDAR detection with point pillars, and segmentation, some segmentations also. In the processing subsystem, we have implemented operating system and the host applications like sensor fusion core, 10G logging with GPS, IME and CAN-FD handling done on the RPU. The choice for the distribution of these workloads on this specific compute domains is for example, matrix compute goes into the AI engine. Hardware time protocol are implemented on the programmable logic. Those components like GPS, IMU that require hard real-time constraint goes to the RPU, and the main automotive grade Linux goes on to the APU. So this was the current ADAS architecture that we have implemented. So the next portion, when we're going to migrate it into the Gen 2 devices, what are going to shift, what components are going to be implemented in the newer section or arranged around, that is shown in this table. The first thing is we're moving 5 of the PL blocks to the hard IP. The ISP pipelines move to the hard ISP tiles. The video decoder and encoder moved to the hard VCU. Previously encoding was done on the PL, only decoding is in the Gen 1. The HDMI TX IP that is instantiated in the programmable logic will also be moved to hard display port 1.4 controller. So the protocol change is here. The MIPI IP moves to the hard MIPI C5, and the OpenGL visualization server that was running on the APU will be moved to the graphics processor. So all of these shift to the hard blocks will save a lot of PL resources, which can help us add some more sensors into the system. Next is the AI engine custom kernels will be implemented for the newer AI ML V2 architecture, which doubles the per tile throughput. So for example, let's say some of our kernels required 20 AI tiles to get a certain amount of performance. In the Gen 2, we're going to get same amount of performance with a reduced amount of AI engine tiles. Let's say around 14 to 15 tiles will be sufficient for that previous kernel. Also, the newer MX6 and MX9 data types will be more efficient. The APU also becomes ASIL-D capable, and the RPU's GPS and IMU CAN paths will be moved to the Cortex 52, which actually remains the same. Also, the memory bandwidth will be improved because of the DDR5. So this is the uh, like components that we're going to move in the Gen 2. So finally, the main takeaways from this webinar session is Versal has three compute domains with network on chip that eliminates the sensor bandwidth inference and real-time control bottlenecks that we might get in the previous MPSoC architecture. The programmable logic, AI engine, APU and RPU each has a distinct role to play in the ADAS application use case, and the availability of network on chip makes all of this system to work as one possible. The camera ISP, LiDAR processing, CNN inference, sensor fusion and ECU communications all run parallelly on a single chip. The Gen 2 moves 5 PL systems to the hard IP and also upgrades the safety chain to SLD for whole end-to-end pipeline, so that the system can be certified for automotive grade application. Also, the AI engine efficiency is doubled per AI engine tile. The network on chip quality of service allocation is very important. If we get it wrong, we can get some pipeline stalls, and if we're able to optimize, we can just get the right amount of throughput for each of the data routing. So these are the key takeaways in this webinar. Next, we're going to go through the frequently asked questions that we have got from our customers regarding the Versal devices. What is the range of Versal AI Edge devices and which evaluation kit should we start with? The Gen 1 AI Edge family consists of 7 devices starting from V2002 to V2802. The AI tiles scales up from 8 AI tiles to total of 304 AI tiles in the largest size of the device variant. For evaluation board, the evaluation board provided by the AMD is VK280 for Gen 1 devices, and the equivalent evaluation board for Gen 2 is VK385, both of which are in production and can be purchased, and development can be started. Why choose Versal over an edge GPU architecture? So couple of the points that Versal is advantageous compared to a GPU plus other device architecture. First one is we get lower power for the full pipeline because Versal handles the sensor interfaces, AI inferencing and real-time control on a single chip without needing a separate device for the IO, which a GPU cannot do natively. We also get deterministic low latency because ML workloads runs on the AI engines and sensor pipelines can run on the dedicated PL, so the worst case timing can be bounded. We also get the adaptability because PL fabric lets us build any sensor interfaces or custom pipeline logic for our specific application in the hardware itself without accepting a fixed set of interfaces. Third question is what are the downsides of going with Versal? There are a couple of challenges, I would say, rather than downsides. One is we need to mostly develop the architectures ourselves. There is not a lot of open source ecosystem that we can combine compared to let's say an NVIDIA Edge GPU to get started. But at the same time, this trade-off can also be a strength. The components and architecture we build gives us full control and flexibility that is tailored exactly to our own application, and we also do not need to be dependent on someone else abstraction layer. So what we get is higher development effort, but we have complete control in the development of the whole system from the hardware level to the software. How do we migrate an existing MPSoC design, and what carries over automatically? It is not a straightforward one-click migration. So the configurable logics, DSP blocks, and most of the on-chip memory can be used as it is, but the XZ interconnect, transceivers, and Ethernet MAC design might have to be rebuilt. Uh, One of the best approaches will be to start a project from the scratch targeted for the Versal devices, and take the components for or the PL logic as it is, but also we need to re architect the system for the routing to go through the NOC instead of the XZ interconnect. So we might need to redesign and restructure the whole MPSoC based system. Do we have to use the AI engine, or can we build with just PS and PL? The AI engine is optional. We can definitely build a virtual design using only PS and PL, using the same Vivado flow as in the Zinc MPSoC. Also, the AI engine is only present in Versal AI Edge series and AI Core series of devices. There are also Prime and Premium series in the use cases where we do not need AI engine. We can use those series as well. How flexible is AI engine development, and when do we write custom kernel versus using YTCI? We can program the AI engine in C and C++ using the ADF graph API, which speeds up our workflow for ML workloads considerably over writing, say, an RTL design. The full simulation flow runs on x86, so we can validate the functionality of the kernels before testing it on the hardware. On the topic of whether to use Vitis AI or create a custom kernel, if the available CNN networks or neural networks that currently you are using is supported in the Vitis AI, it will be much faster to directly use the Vitis AI. Also, if the performance and latency requirement is fulfilled, then Vitis AI is preferred. But in the case you have a custom network and the performance is not fulfilled by the Vitis AI or the NPU, then in that scenario AI engine kernels can be custom written for that neural network. Also, if you have some use cases or workloads where it is not a standard operation, you have a signal processing stages mixed with inferencing, and also you need the direct or complete control over the tile level data flow, then also the custom AI engine kernel creation is recommended. In our own ADAS system, we have written custom proprietary kernels for the all the LiDAR pre-processing pipelines before the data is fed to the NPU in the AI engine. Can we run multiple neural network models at once on one Versal device? Yes, we can load and run multiple models concurrently in the Vitis AI NPU. We can also instantiate multiple custom AI engine kernels that can run concurrently. In our own ADAS system, we are running both NPU and custom kernels parallelly, and these are being managed through the APU. How do we deploy a PyTorch or TensorFlow model on Versal using Vitis AI? You can go through the Vitis AI user guide. It has complete flow description on how we can start by testing a PyTorch model and quantizing and compiling for the Vitis AI NPU. The whole flow is in the Vitis AI user documentation. Also, the AMD provides different tutorials on their GitHub repo for this deployment processes. How do we configure NOC QoS for a multi-camera pipeline? We can configure the NOC NOC in Vivado block design. We can set different bandwidth and traffic classes depending on the data pathways. Currently there are 3 traffic classes: low latency for high priority read traffic, isochronous when we need latency guarantee, and the best effort, which is default, and it tries to give the bandwidth resources in an equal manner. For a multi-camera pipeline, we assign best effort to the camera ingest DMA, isochronous to the AI engine streaming paths, and low latency only where we specifically need to read data at a very fast rate. We also treat this allocation as the initial stages during design, and draw out a NOC specification beforehand. Because the AI engine and PL uses a separate NOC paths, we also have our camera streams and inference running at full throughput when the bandwidth is specifically allocated for those. The last question is what ACL level can Versal support for an ADAS application, and what does it cover? So it depends. In the Gen 1, the RPU in lockstep supports an ACL B certifications, but in the Gen 2 the coverage has been increased, but it is split between different components. The APU, the processing system, NOC and memory controllers can be certified up to ACL D and CL3. The Mali GPU, AI engine and ISP are targeted for ACL B and CL2 certifications. So this means we can build a full ACL D path for fusion, control and vehicle communication from the sensor fusion core through the NOC to the CAN output without the need of an external microcontrollers. Since the inference itself runs on the AI engine, which is targeted for up to ACL-B, so if our safety case needs perception output that needs to be certified for ACL-D, then that requires a careful safety case study and might need a few redesigning also. So these were some of the queries that we have got while we were working with some of our customers. And also if you have queries regarding this, you can mail to us. So this was our Versal AI Edge webinar for the ADAS, and thank you.